For our final case study, let's consider the acylation of bromobenzene. This reaction is slow compared to a comparable reaction with benzene, which illustrates that bromine is a deactivating group. The electronegativity of the halogens explains this effect. Halogens inductively withdraw electron density from the ring. The resultant dipole renders the ring electron poor. Notice that the partial positive side of the dipole is on the same side as the aromatic ring. And the fact that the ring is electron poor means that it will be a weaker nucleophile than benzene, and it will perform an EAS reaction more sluggishly than benzene does. However, resonance is in competition with the inductive effect in this instance, and resonance, it turns out, explains the directing capability of the halogens. Despite the fact that they are deactivating, halogens actually direct ortho and para. So you can see that the products of this reaction are the ortho and para regioisomers. Let's examine why that is the case. If we simply consider the resonance forms of bromobenzene, it quickly becomes apparent that the ortho and para positions are the most electron-rich and therefore the most nucleophilic. These are the sites that will preferentially undergo EAS reaction. While the resonance structures foreshadow the directing effects of the halogens, let's also go through the complete mechanism in order to further rationalize the outcome. The mechanism begins with Lewis acid-base reaction between the acid chloride and aluminum trichloride. Then, aluminum tetrachloride anion dissociates to form a positively charged acylium ion, our potent electrophile for the EAS reaction. The attack of a pi bond of bromobenzene on this electrophile could place the new substituent in the ortho, meta, or para position. Let's take a look at the ortho-para pathway first. Since these pathways are electronically equivalent to one another, we need only draw one mechanism, and it's the para pathway that I'll be showing here. The para-sigma complex has not only the usual three resonance forms that move the charge around the ring, but also an additional resonance structure in which bromine donates electron density to move the charge outside of the ring. This last resonance structure is especially stabilizing because all atoms possess a complete octet. It therefore lowers the energy of this pathway, thereby favoring it. Note that the exact same phenomenon would occur in the ortho pathway, and in fact it's a wise idea to pause the video at this point and to draw out the mechanism for the ortho pathway to convince yourself that the sigma complex has four analogous resonance structures. The mechanism concludes with loss of a proton to a chloride that dissociates from the aluminum tetrachloride anion. This generates the para product, and as we've noted previously, the ortho product would result from a similar pathway. Let's take a quick look at the meta pathway to see why it is not favored for this reaction. The formation of the meta-sigma complex is shown here. Although this sigma complex does have resonance, there is no opportunity for the halogen to participate in delocalization of the charge. So this sigma complex has only 3 resonance forms contributing to the resonance hybrid. When we looked at the ortho-para pathway, we saw that there were 4 resonance structures contributing to the resonance hybrid for its sigma complex. This shows why the meta-sigma complex is higher in energy than that found in the ortho-para pathway. To recap, the halogens present a bit of an anomaly. They deactivate the ring toward EAS by inductively withdrawing electron density. Most groups that withdraw electron density from the ring and therefore deactivate it toward EAS also direct further substitution to the meta position. The halogens, though, are unique in that they are deactivating toward EAS but direct further substitution ortho and para. The next video in this series will conclude our discussion of the effect of substituents on EAS reactions. We'll summarize substituent behavior, discuss problematic Friedel-Crafts reactions, and consider the EAS reactions of disubstituted and polysubstituted benzene